Welcome back, humans and robots alike. Today we'll be talking about that factor graph approach of Bayes estimation, and we'll look how we use this EIF matrix which we found in the last discussion to be implemented in the Emily fashion, Emily estimation or map estimation. Emily, I mean maximum likelihood estimation. Just misspoke expression, guys. Also, we'll look at how factor graphs are this cool little way of representing SLAM problem statement. And I remember this one quote where like every CS grad ends up looking, after some time, ends up looking at the world just a bunch of graphs, right? And which should tell you how important this factor graph approach could be in SLAM, especially for the modern methods. And then we'll also look at how we can use this map estimation using for SLAM using both linear and nonlinear optimization. And also look at some few cool little results to figure out the difference. So initially, people tried to do this optimization based SLAM. So you have all these landmarks which you detected, all these poses which you had, the iteration, the motion models, the control inputs. Take all of that information, the whole overall runs information, and then try to optimize a trajectory or poses as best as you can. But early attempts were miserably uh, bad because the computational cost to do all of this is it's really high, and real-time systems want things to happen quite quickly, and that became a bottleneck. But when people saw this information matrix, which we discussed last in the last lecture, it gave them a bit of a thumbs up that no, like you can still do this, and that whole thing led to Emily. So that's your maximum likelihood as well as maximum a posteriority estimation based methods. So we'll look at it. Uh, let's first figure out what factor graphs are. So it's usually termed as this like the language of so factor graphs is usually said to be the language of SLAM. In this language of SLAM, you have basically two kinds of vocabulary, right? One are your variable nodes, the other are your factor nodes. We'll look into this. So initially, to just set a picture of what this factor graph is representing, you have P1, P2, P3 poses. At P1 and P2 pose, you can see this landmark L1, so you have that dotted line. And then at P3 pose, you can see the landmark 2. The directed arrows between P2, 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 P1, P2, P3 are showing how the poses, I mean, how the positions were incremented, successive poses were gone through. In this, we are obviously assuming that we know our position where we started off with. We also know with some probability where the L1 and L2 are. Unlike earlier approaches, we are going to assume probability from the base. We will not try to modify Kalman filter or some other method to work with probability. No, we are going to assume probability from the get-go. And because we are doing that now, what we have with us is this PDF function, which is probability density function. So Px iterated over the whole states x should equate to 1. So that's just the condition we need to remember. Now, in this, we have two types of, as I said earlier, right? Vocabulary in this graph language of SLAM, you have two types of things, variable nodes and factor nodes. Variable nodes are all your poses, your landmarks, all included. Factor nodes is what tells them how the connection happens in between these things. So assume them to be nouns and then verbs or adverbs, right? Factor nodes being the verbs or adverbs. Let's call them verbs. So great. I think you guys have a plan. So let's try to figure out, given this graph, example graph, SLAM graph, which we have factor graph, what is the probability of being at some state X, given all the sets of observations which I have? And those black circles are basically denoting factor nodes, and we'll populate them slowly, step by step. So initially, we we know that we are at position P1, and this probability that we are at position P1 would be a lot higher, maybe towards the 99% or something. But anyways, so we have this P1 position probability. Now, at P1, we see there's a landmark. So there should be some probability at which we know that this is the landmark and also the position of this landmark or pose of this landmark. That's where the probability PL1 will come into play. Then obviously the interrelation between the two, oh, given P1 and landmark 1, what was the probability I would get this observation, right? So that is also something we need to consider because there could be a case where, I mean, though we are considering this PL1 probability, there could be a case to made that I didn't detect it properly or I don't always see this landmark properly. So landmark's position could be known with some uncertainty, but to detect the landmark also there will be some uncertainty, right? Even if you use any deep learning method, it's, oh, I am this much accurate or this much sure about this being a particular object. So that's what that PZ, I mean P observation conditional to L1 and P1 plays a role there. Then we go from P1 to P2, how the state updates, that probability comes into play. And then the probability of, oh, being at P2, what is the probability I would have seen L1, and then P3 I go to, and then PL2 comes into play, and then the probability of observing PL2 given this particular landmark, I mean the L2 landmark and my pose P3. So we see that a particular state given a condition to a particular given a condition to a particular set of observation can be predicted in this product of factors fashion. And that's where that's a very important point to understand that we're going to work with this term called as product of factors a lot, multiplicative, right? Why, you ask me? So there's this thing called as map, where what you want to try to find is, I want to find the particular state which has the maximum a posterior probability. So what you see in this first set of equation is, given set of observation, what state has the highest probability. I'm not trying to find what is the highest probability, but rather associated with this highest probability, what is the state? And that state becomes the X map state or the maximum a posterior state. Right. So using my good old Bayes theorem, I will expand this Px conditional to Z term in this fashion. Using this, I can just ignore the PZ term because it's kind of like a scaling term, don't really care about it, and then just use this term, in general. Now, given this term, let's see how we will deal with things coming along. This is again, so this is more of setting this whole thing into a formal way. So I have variable nodes, factor nodes, and then the edges between the two sets. These are uh, two sets I have. One represent variable nodes being U, one represent factor nodes being V, and then E is an edge between that. So that's how our factor graph comes into or gets built basically. And then the X map would be found by just multiplication of these factors which we have, right? This is what we can even see from this observation. That is just multiplication of the factors. So great. We know how to do that. We did it in our toy example, right? Okay. Now, uh, I'm definitely going to uh, have some sort of a distribution curve. In this, again, I'm just assuming an Gaussian distribution, and where I'm just going to take into I'll remove all that scaling stuff which I have and just talk about that exponential term. So given my particular measurement and also this measurement prediction function which I have, it could be nonlinear, right? The HI can be nonlinear and probably would be nonlinear. So that measurement prediction function will come into play there. Given this, I will just take logs on both the sides, remove the -2, and this is the term which I would get. Now remember, we had removed the -1/2, and then so if you take log of this multiplicative term is additive, and because you're taking minus out of it, the argmax will become really an argmin rather. Okay, so far so good. So we have gotten to a place where we can use some sort of optimization functionalities. But right now, still the problem is the HI is non-linear in nature. Now, One way would be to linearize it. That's the EKF way also, if you remember. I can use the Taylor series, uh, linearize this particular set of equation. My xi0 would be the linearization point, blah, blah, blah. So this math we have somewhat of understood, right? Now I can take this equation, so this part and then this part, I can take this and add it to my overall equation. Now here what I see is I'm trying to club two terms together. So the Zi and Hixi not term, I'm trying to club them together. And also my Hi, this term basically. Now important observation again here is because I have square, I can just do minus of it. So this can become here and this goes to here. And why I wanted to do that is because if I reshape this whole equation of mine in this fashion, the A matrix becomes a sparse. It's large, but it's sparse in nature. And we know that if an equation is sparse, I mean, if a matrix is sparse, it becomes a lot easier to take inverse and do other matrix calculation on. And that is exactly what we need. So now we can use Chomsky factorization, which is basically using information matrix stuff to minimize or I mean find this normal equations answer. Either that or we can use QR factorization or some other methods to find the solution of this particular normal equation which we have, right? Okay. Another way to solve that particular nonlinear equation is to use nonlinear optimization techniques. So we can use steepest descent, Gauss-Newton, or LM method. Will in our results, which I'll show you in just a few minutes, I'll be using the LM method, right? Again, so you can look into what these methods are and how they work. Just because of the time constraint we have, I don't really talk about it as much, but we can definitely go and look into it. And they will be included in lecture notes if somebody needs to understand that. So what do we gain from doing all this? So if you look at the output from MAP versus the output from EKF, you see that the EKF estimates can go bad a lot of times when erroneous data comes in very crucial times, right? Erroneous observation comes in very crucial time to this system of EKF. Whereas MAP, because it's considering all the observations, it is a lot more robust to these small variations, small and crucial time variations which come into play. And also because it's trying to approximate over a period of time and over all the observation set which you have, its accuracy is also a lot better. So the RMSE error or the MSE error which you see of EKF and MAP can see a vast difference between multiple different runs. Sometimes it goes way too much. Sometimes it's okay, but it's still quite far away. And that is the observation which I wanted to showcase. Now again, this talks about so you are doing it overall, the overall trajectory, and then EKF also relies on these initial noisy guesses, which is what we saw in the last lecture, right? Where the initial estimate, if the motion model is too bad when you predict or when you see a landmark, and because you're just taking that into consideration, estimate of that would be a lot more noisy, and so you don't reduce your covariance by a lot in those circumstances. But EKF has that problem. MAP does not because it takes in consideration observation over the time, right? Over the whole period of time which you have. Again, that basically also means it's expensive to run. You might be using information matrix, you might be doing a lot of optimization. It will still be expensive to run. Accuracy is still going to be higher. Consistency with my overall trajectory is going to be better, but at a cost of complexity. So with this, I hope you got a bit of an understanding of how factor graphs work, what its advantages are, what its disadvantages could be. And again, it's the language of SLAM, so I hope everybody can start speaking back now. With this, we'll conclude the session. I hope to see you guys in my next lecture. Thank you.